So I'm Dave Cohen. I'm at Intel. I work in the non-volatile memory and storage solutions team. We're the group that's bringing the Optane DC persistent memory to market. This talk is about the storage architecture of a platform we're developing. We call it the data management platform. And I'm going to do the talk with Phil Reisner from LINBIT. So this platform is an integrated hardware software solution. It's rack-centric design, and it's designed to scale out at the rack granularity. So it scales to about 16 racks in a 3-stage Clos today. This is really driven by a set of end-user pain points that we did a bunch of discussions with end users over the last couple of years. One of the big driving forces in the market right now is this adoption of data as a revenue-generating enterprise. So data under companies' control, they start to look at using AI and analytics. And the problem with that is that accelerates their data growth rates, and especially on higher performance storage. This leads them to the decision that they need disaggregated storage because they want to scale compute and storage capacity independent of one another. The problem with that is it's really messy to do that on your own. Like there's a lot of heavy lift to make all that work at large scale. And then the last piece that we heard from everybody was they want cloud-like open source analytics and database-ready infrastructure. They basically want public cloud, but the customers that we're targeting are people that want to deploy this on-prem. So how do you actually give them Amazon Aurora or Elastic MapReduce on their own prem? And the answer, of course, is disaggregation. But what is disaggregation really? Well, this slide really just wants to level set that disaggregation is a function of networking, right? This is circa 2010, and James Hamilton's waving his hands, saying the network's in his way. A couple years later, Andy Bechtolsheim's at Nanog saying, hey, the network's on the way to getting out of my way, and this is going to unleash non-volatile memory innovation. So we at Intel have been looking at doing this at rack scale in the rack scale design or rack scale architecture, was I think called previously. So what a rack looked like yesterday was it was really built around hyper-converged infrastructure, Hadoop, Google, et cetera, but it had locally attached drives. And you scaled compute and storage in fixed ratios. In order to disaggregate, though, what you want to be able to do is take bulk storage, take disks effectively, and remove them from the compute so that you can scale compute independent of storage. At Intel, what we want to do is do that in the context of Optane technology on the compute side. And on the storage side, we want to do that with QLC. So we want to displace hard drives with QLC NAND NVMe devices. And so this is kind of just product positioning. So in terms of where we've been investing money for driving innovation, it's really looking at it from the storage tiering standpoint. There's a capacity gap on memory side, and that's where our Optane DC persistent memory product, our DIMM product, is positioned. And then there's a performance gap and a capacity gap in the context of these racks. Most data centers that are not the big CSPs have crappy networks, right? So how do you build a cluster inside those crappy networks that is effectively an island of bandwidth? A cluster where you have effectively all the bandwidth you need. And what that means is I need to place the data there with high capacity and high throughput. And that's where the QLC NAND comes in. And then I want to be able to provide an extension to DRAM to address capacity. And that's really where Optane's positioned, both in the DIMM form factor as well as in the NVMe form factor. All right, so really quickly, I'm going to show you the stack, and then I'm going to turn it over to Phil. So the stack is, like I said, rack-centric. So each rack comes with basically a leaf and spine switch. These are 32-port, 100 gig switches. They're pretty cheap, actually, today. The bottom gold boxes are storage servers. Those are pretty much commodity servers. You can attach JBOFs to them, or you can just use 4 NVMe drives per CPU. But the key ingredient here is that we have 4 to 8 NVMe devices for 100 gig NIC in a CPU. With 4 NVMe devices, you can saturate 100 gig NIC. So those black lines are each 100 gigs. On each storage server, we have 2 100 gig NICs, 1 per CPU. Then we also take a 100 gig port and we split it into 2 50s. Every compute element has a single 50 gig NIC and some local Optane. And that's basically the physical cluster. We run BGP to the host, so everything is routed. So the software stack, we designed this from scratch to boot into Kubernetes. So the bottom of the stack, you can see we kind of isolate and pool CPU and DRAM, networking, and storage, where storage includes compute side Optane, and then the QLC NAND. We then use a virtualization layer that is fundamentally Kubernetes-based. So we use an SDN implementation and a software-defined storage from LINBIT. And then we boot that into Kubernetes for orchestration. Our core storage is basically managed local scratch, ephemeral scratch on the compute side, cloud-native object storage, and cloud-native event streams. So think Kafka and S3 effectively. And then the workloads we're targeting currently are AI and analytics, predominantly Spark and TensorFlow. And then databases, and I just used MariaDB with a changed data capture system, Spark, Presto, et cetera. Those are the kind of workloads that we're targeting. And I should say these are all open source components. And then I'm going to turn it over to Phil, and he's going to take you through the core storage implementation.
Thank you, Dave. Yeah, so so LINBIT is a comparable small organization when I compare it to Intel. So we are about 30 people, and you might know us for DMP. But I need to put forward, DMP is not used in this context. So move that aside for a moment. These days we are working a lot on a component called Linstore. And Linstore is a storage orchestrator that's all open source. And it is here to manage your storage and using a data path technology that fits your problem. So in the context where we're working with Intel, the data path technology we're using is NVMe over fabrics. In other projects, it might be DMP or something else. So the Linstore software has 2 major components. So one we call the Linstore satellite. You could also call that the node agent. And in our case, the Linstore satellite, that's the same thing. regardless if it runs on a storage node or if it runs on a compute node. Just as a side note, we also support hyper-converged hardware ideas, which is not the case in this project. So in this project, everything is nicely disaggregated. So apart from the node agent, there is the central component. We call it the Linstore controller. Just as with the previous presentation, you usually run it in a three-way redundant setup, the central component. And and on top of that, you have a command line interface to interact with your system. And we have a number of drivers that connect us to higher levels of the stack. In this context, we're only talking about Kubernetes. So right now, we're using the Flex Volume driver in Kubernetes and an external provisioner. The CSI work is already done, but it's one of the next steps to switch our work we do with Intel from Flex Volume to CSI. I grayed out the areas I'm not talking about, so just very briefly, Walserhoff drivers for Cinder, for smaller players in the open source world like OpenNebula and Proxmox. These were important for us to find our first users and customers, right? Also these smaller ecosystems. Yeah. By default, we have, this controller doesn't deal with a lot of data. It's just a couple of 100 bytes per node and storage device. So by default, it comes with a embedded database, but if you wish so, you can also run it against external databases. Okay, so what is it doing? What problem does it solve for you? So it does the volume placement, and in what we're doing here is we're not attaching complete physical disks to the compute nodes. We are attaching volumes to the compute nodes. So in essence, we're using LVM on the side of the storage nodes to carve it up into the pieces we need. And then we use NVMe Fabrics target and initiator to give it to your compute node in the unit you need it, right? So one of the problems it solves is the volume placement. So there might be a number of constraints on your volumes, like you need a couple of volumes for your MinIO containers, and then you want these volumes to be in independent failure domains, right? Because if you lose one of these NVMe drives, it should only affect one and not all of your containers. So there's a lot of constraints behind the scenes you need to get right. So for that, we have these arbitrary tags, and then you assign rack numbers, room numbers, sites, etc. to your objects in the system. And then you can express pretty arbitrary placement policies that works on the values of your arbitrary tags. That's on the side of data placement. The other thing we need to place is the network paths, right? So in the context of the work we're doing with Intel, the nodes are usually equipped, well, the storage nodes are usually equipped with 2 NICs. And each of the NICs goes to one of the processors, right? So what you want to do is when we export the volume from here, and then the SSD is attached to one of the processors, and we want to use the NIC on the same processor to export it. We don't want to cross from one processor to the other with all the data. So that's the easy part. in other projects, the selection of the NIC and data path and eventually having multiple data paths is a bigger challenge, but not in this context. Yeah, so that's the basic explanation what we're doing here. So I really want to repeat these 3 points I have here on this slide. So Linstore is this control component for attaching storage or providing storage in a software-defined storage way. And we are talking here about block storage, right? It's not objects or files. It is built around all the storage functions we have in Linux. So in this context, it only uses LVM and the NVMe target and initiators. But we're also looking at the Ubuntu world. There they want to use CFS and C volumes from that. Sometimes you want to have your data encrypted at rest. So we control decrypt. We will come up with support for the deduplication technology, the two caching technologies with the kernel, all of that. So the idea is that Linstore will control all of that. Not everything of it is already implemented. So you find here the roadmap at the bottom of the slide. And yes, I really want to stress it is open source. So you find it on GitHub and it's GPL. Yeah. So talking about the roadmap for a few minutes. So right now we're using the SNEAS Wordfish API to talk to the storage nodes. In the context of NVMe over Fabrics, we are in the process of enabling using the native Linux mechanisms. So in a sense, touching directories and files in sysfs on the target side and using the command line client on the initiator side. Then, yeah, some work to enable the obtain DC persistent memory that's still ongoing and is going to be merged in a few weeks. Then right now, besides the command line interface, there is a Python library if you want to interact with it. And that's not the most generic interface in the world, right? So it gets a REST API as well. And then there is, more interesting stuff going on. Okay, I think in order to keep our 30 minutes.
All right, thanks, Phil. So a couple of things, I'm just going to go real quickly back to this picture. Just to give you some concrete implementation, our network virtualization, we use Calico, and Calico provides a CNI. Like I said, we route to the host. So we control the bandwidth both horizontally within the rack. We do not route NVMe over Fabric outside the rack, so it's all rack local. We do, however, allow for applications running on the compute side to do all their horizontal replication or distributed erasure codes across the cluster. So you have kind of traffic going this way, you have traffic going vertically, and then you have incoming requests from clients. So a big part of this is really how do you do network control and partitioning. And then we just went through the LINBIT piece. And so real quickly then, a performance snapshot. What I wanted to get across is 3 basic fundamental concepts. The first one is, like I mentioned briefly, we saturate a 100 gig NIC with 4 NVMe devices. These are Gen 3 PCIe, so at 3.2 gigabytes for a by 4. And 4 of those will saturate the 100 gig link. We do this by partitioning each NVMe device into 16 logical volumes using LVM and device mapper. And each one is given 200 megabytes per second SLA. And so we just scale that up, and you can easily saturate the 100 gig NIC. And so that's exactly what we did in this test. And we can do this across an entire cluster, 16 racks, north of several hundred machines. And Chris Banier did all this testing, by the way. Chris is out in the audience, so thank you, Chris. The second test that we do all the time now is we want to be able to show that you can saturate the 50 gig NIC on the compute side simply by scaling up the number of concurrent logical volumes running. And so that's what this test shows. And so this scales out across the racks, JBOFs, and NVMe devices. And you can see scaling up to 32 devices will saturate the 50 gig link. And then the final test here that and then I'm going to jump to the workloads, is distributed object store. The interesting thing about Minio is very much like Facebook's object store that replaced HDFS. It uses synchronous erasure codes, so it gets rid of three-way replication in favor of distributed erasure codes, but it's all done synchronously. Very, very high throughput. This allows us to basically take an 8+4 erasure code stripe, distribute the Minio nodes in that cluster, so 12 Minio nodes, each with one logical volume, distributed across the cluster so that everything is fault tolerant. Minio uses an internal quorum for reads and writes. And in this way, we can scale out and deliver about 1.5 gigabytes per second for a single bucket. In our context, a single bucket is isolated to 12 Minio processes. So if you add buckets, you're adding Minio processes as well. And this scales to basically, if we run no other workloads, we can scale the number of Minio buckets until we saturate all of the bisectional bandwidth. And that starts to go about just north of 24 Minio buckets in the configuration that we used. And that turned out to be some constraints or some miscabling of JBOFs in the test bed that we were using. All right, so then just a couple words on workloads. The first one is the work we're doing with Spark and TensorFlow. This replaces HDFS with the S3 backend from Minio. And then we're able to run workloads and data set sizes that rival kind of mark to market with, say, Facebook machine learning 3 years ago, which was about a 100 terabyte data set. And performance on these is pretty close to what you would expect for the type of cluster we have here. I don't have any formal presentation of the performance numbers. I can say that we've been working for over a year with a lighthouse customer. They see about a 60% improvement over their Hadoop clusters with local disks. The second workload that we're focused on is database. Intel policy. Is a cloud-native database. So we basically have worked with the MySQL community and using Facebook's MyRocks storage engine instead of InnoDB. And effectively, we took RocksDB and we worked with the team that developed Rocks. They spun out of Facebook and have a company called Rockset. But Rockset has a RocksDB cloud library that allows us to map SS table files, so effectively snapshots, onto S3, and the write-ahead log from RocksDB onto an event stream like Kafka. What effectively that allows us to do is maintain a consistent image of the LSM tree on the network, which allows us to move the database from one host to another, which is very well suited for running cluster-wide Kubernetes. So, and that's all the time I have. I guess real quick, one question. Any questions? Very good. Thank you, guys.
I have a quick question. This is the LVM. So you, in your performance example, you said you broke up the LVM to match the performance. Is that kind of the desired embodiment of, so the LVM, you said you were using the LVM to maximize the performance. What if there's like an application that needs twice as much capacity as another one? Like how does that, kind of flexibility work?
We really target more the workloads like Amazon Aurora or EMR, where the capacities are really workload driven. So it's much more of a SaaS platform than it is infrastructure or service.
Okay. So doing it by performance is the preferred, is the only way to do it. Okay. Anybody else?
So on the previous slides, you showed the storage servers connected to the JBoss and the containers. So we're just wondering the specification of the storage servers, how many cores?
So we're using Skylake 6150s in this current test bed. We're in the process of moving to Cascade Lake. There's a lot of ways to do that. You can do lower end, and then as long as you have enough PCIe lanes, that's the main. Okay. Thanks, everybody.